Excellent. Lesson 8, PBoM. We're going to talk about the gas laws, kinetic molecular theory, and what is an ideal gas. So our learning target here that we're trying to focus on is understanding how kinetic molecular theory relates to gases, pressure, and molecular collisions, as well as describe the behavior of an ideal gas with respect to temperature and pressure. So big picture, we're just trying to get an overview of what these gas laws are and how gases behave using these theories. So kinetic molecular theory says a few things, little facts that we have to assume and put in the back of our head. Okay, gas is a collection of small particles traveling in straight line motion. That's the first assumption. Secondly, these molecules of gas occupy almost no volume. We're going to ignore the fact that they do probably have a volume, but they're so stinking small, they're almost like two-dimensional points in space. We're not really even going to think about them as having size. Okay. Collisions between these molecules are perfectly elastic, which means that when one bumps into the other, no energy is wasted or lost in this collision. Okay, and I think the last thing we say about that, well, it's missing in there, so don't you even worry about it. Okay, there are no attractive or repulsive forces between these molecules. It means that they're not trying to stick to each other, not trying to share electrons with each other or anything like that. These molecules literally don't want nothing to do with each other. They're moving in straight lines. When they bump into each other, they transfer their energy completely, and they practically have no volume. Those are the rules of KMT. But what conditions make a gas behave like an ideal gas? Because that KMT theory is a theory. Truly, gases behave differently, but it's useful for predicting the behavior of gases under most general conditions, when those conditions allow the gas to behave like an ideal gas. So in order to be like an ideal gas, you have to have conditions close to the kinetic molecular theory. So your molecules of gas should be very small. H2 is a perfect example of very small gas molecules. There's the smallest gas molecules that we can think of, because hydrogen is like one of the smallest elements. Okay, small particles, small molecules, high temperature. So you heat that gas up so that those molecules of gas don't want to stick to each other, and they move in straight lines very well. And then low pressure. The lower the pressure, the less likely these are to stick to each other. Okay, if we have sticky molecules, we're not ideal. So to be like an ideal gas, we heat the gas up and we put it under low pressure, and we want to make sure we have a small gas that we're talking about. More complex molecules, this theory starts to break down, and you need more advanced chemistry and calculus to figure out how the gas behaves. But we don't go there. We stick to the basics here. Okay, so the individual gas laws, these were combined into what we call the combined gas law, but I want you to understand what the relationships are. Most of these are intuitive, and you might know them already, but you don't know their names. So the first law is Gay-Lussac's law. It says that as temperature increases in a confined space, so like a sealed container, right, the pressure will increase if we're talking about a gas. Let's think about that. I got a soda can, it's sealed up. If I heat it up, the pressure in there increases to the point where the soda can eventually explodes. Okay, it makes sense. A graph of this, the inverse is true, obviously, as well. So as the temperature drops, the pressure is going to drop as well. Sorry, I was getting ahead of myself. The graph, though, is a direct relationship, and it looks a little bit like this. As temperature increases, pressure increases as well. It might not be a perfectly linear relationship, but that's what happens. Higher temperature, higher pressure. Lower temperature, lower pressure. Memorize that. Okay, move on to our next law. Charles's law. As temperature increases at constant pressure, volume increases. So keeping the pressure the same, but allowing the volume to expand or contract, like in a syringe, okay, or a balloon, all right, is what's happening. So as you heat it up, the gas expands. As you cool it down, the gas contracts. And that's the relationship. It's another direct relationship, but it's positive. Yeah, I was going to say it's negative. Nope, it's not a negative slope. So as temperature increases, volume increases. As temperature drops, volume drops. Okay, that is Charles' law. Boyle's law. Boyle's law says as pressure increases under constant temperature, so you're not letting the temperature change, the volume will drop. So if you pressurize a gas, its volume decreases. And the opposite's true. As you drop the pressure, the volume increases. Okay, so it's actually an inverse relationship. So this slope will be negative. Not exactly a perfectly linear relationship like this graph is showing, but definitely a negative slope. Okay? The last gas law, Avogadros Law, it says that the number of moles of one gas is going to be equal to the number of moles of another gas if temperature, pressure, and volume are the same. So two identical balloons, temperature, pressure, and volume are all the same, two different gases inside of them. Well, there's still the same number of molecules, moles, in each balloon. Even if this is hydrogen and that is helium, same temperature, same pressure, same volume, same number of particles. That's Avogadros. The combined gas law, Avogadros law says 1 mole is 22.4 liters, period, end of story, at STP. The last thing, I'm going to summarize our lesson, pressure. Heating an aerosol can, boom. Heat it up, pressure increases, kaboom. Temperature. Cooling a balloon down, it contracts, simple. Volume. Engine cylinder. As you compress the cylinder, the pressure inside there increases to the point where it explodes the gas. Important. And number of moles in gas. Inflating tires. As you pump more air into the tire, you're putting more molecules of gas into the tire. The tire's pressure and volume both increase. Kind of simple, straightforward. That's it. In the next lesson, I'm going to talk to you about the combined gas law. So taking all these general relationships and putting them into the equation that we actually have to use when we're doing calculations related to gases. Okay, so thanks for watching. See you in the next and final lesson of this particular series. Hasta la pasta.